things you are saying is modifying the equation and like the between general covariance and this equilibrium equivalence.
Yeah. So the last. Let me remember what I have written. So d2 x mu. So we are trying to write down the equation in the presence of the electromagnetic field, right? Plus gamma mu rho. So according to principle of equivalence, this was given by Q times, let's say, F mu. Yes, yeah, that means this is dx rho d tau. Was this correct?
Yes.
G I used. And then, so this is what follows from principle of equivalence, but then you say that we can simply add some constant A times say R mu rho alpha beta F alpha beta dx rho beta, something like this. Okay, this is perfectly consistent with general coordinate invariance, right? Because you can check that both sides transform in the same way in a general coordinate transformation, assuming tensorial transformation laws for F. But this violates principle of equivalence, because if we go to a local inertial frame where gamma is 0, right, it's supposed to reduce to the standard equation in flat space, but it doesn't because of this extra term. Okay. But the reason that we don't worry about such terms is because this coefficient A has dimension of length square, right? Because it was the same kind of argument that we had earlier. Because you can see that all the dimensions match except that there is an R here, sitting here, right? Everything else is common, right? F dx d tau dx d tau. And R has two derivatives, right? So which means it has two powers of length in the denominator. So this should have a dimension of length square, right? And the natural dimension of length square that you get is what we call L Planck square, where L Planck is like 10 to the minus 33 centimeter. So typically in quantum gravity or other modifications of Einstein theory at the Planck scale, the coefficient that will arise will be like 10 to the minus 33 centimeter square. And this is much smaller than the kind of length scales that we have in for where we test general relativity. And because of this, even if such terms are there, right, you wouldn't see it in today's experiment, right? Because its effect on the kind of experiment that we do to test this equation will be very, very small.
So what we should infer from this is that the principle of equivalence is not very sacrosanct in this sense. Like
yes.
All we have to respect is general covariance.
That's right.
So you can have respective dimensional consistency, you can add more terms which are dimensionally consistent with the other terms.
Yes, you can add more terms, but whatever terms you add,
they have to be suppressed by some.
Typically we will have some additional parts of length, right? So because the point is that this already, so we are looking at the modification of the electromagnetic field equation, right? So there has to be at least one part of F. Okay, otherwise this is a force that is there even in the absence of electromagnetism, which he described in the first earlier anyway. Okay, so there can be, for example, term like what did I write? D mu R mu rho. I had written down some. We need a single power, right?
So d mu r mu rho.
I think there's something like this. Dx.
So it was d mu r mu rho. It's r. There was no mu, only r.
D mu r.
Mu rho means like index of any.
Yeah. The point is
dx mu and d rho means the mu and rho will be contracted by dx. Mu dt and dx rho. Beta also.
yeah. So basically the point is you have to make sure. Let me just write this dx mu d tau that these, and there has to be one free index, so this will be new. Okay, so new has gotten contracted.
So new is already
So
contracted.
that
That
will
will
be
be
new and
and
this will be another term.
mu sigma will not be.
Let me put as a new. And this has sigma. And then it should be okay.
But then sigma is not contracted.
No,
Sigma, okay, I have to put sigma.
no.
This something like this probably is fine. Okay, anyway, you can, the point is you can try to write down terms like this, okay, which involves derivatives and R and derivatives of R or higher powers of R and so on. Okay, yeah, we have to of course make sure that this term doesn't vanish identically by Bianchi. Okay, if it does, you can write down other terms. Okay. But so what I am saying is that these terms are also there, okay, but these terms should be dealt with in as violation of equivalence principle, not in the presence of electromagnetic field, but just violation of equivalence principle without for free particle. Okay, because this is there even in the absence of electromagnetic force. Okay. But in the presence of electromagnetic force, there can be additional terms like this, okay, which would vanish if F was 0. Okay, so these are genuinely there because of the presence of electromagnetic field. Nevertheless, this is not inconsistent with the this is not consistent with the principle of equivalence. Okay. But the corresponding coefficient is small. Okay. And generally, any term that you write of this kind, okay, will have additional powers of derivatives, which means that the corresponding coefficient will also have to be multiplied by some dimension full numbers. Okay. And typical values of those are very, very small. Okay. If these are coming, for example, from quantum gravity corrections, okay, or string theoretic corrections, any corrections that modifies Einstein gravity at a microscopic scale, okay, will have small coefficients here. So the point was that the principle of equivalence is not sacred, okay, but there is a very good reason why it holds to such a good accuracy. Right? It's not something that you have to assume; it's something that you can explain, right, why it works well, and the explanation is simply the fact that there can be violations of principle of equivalence, but those violations you expect are very, very small. Is this okay? So the idea is that it's a generally a good idea to try to get some idea of what equations you should use, okay, to use principle of equivalence to arrive at the correct equation to the first approximation, okay, and then you allow for possible corrections. Right? That's what we did. Right? We assumed principle of equivalence to get to this point, okay, and then we said that we can violate principle of equivalence now by adding covariant terms of this kind. Okay, so the principle of equivalence is a good starting point for arriving at the leading order equations, okay, consistent with general covariance. Is there any other question?
So does this, if you add such terms,
Yes.
then does this mean that space you are treating as every space points are a little bit different now, because you have a R which is sitting always there and it is showing you a difference and you can always observe that.
Yes, that's true. But the point is, it is certainly true that in the presence of a Riemann tensor, every space point is different. Right? You can certainly do experiments, that even within principle of equivalence, you can certainly do experiments which can distinguish different space points. Right? The tidal force, for example, will be different if the Riemann tensor is different at different points. So the fact that you are treating the different space points are different, that is not a surprise.
Even without adding this term extra.
Yeah, even without adding this term, you can certainly perform experiments which can measure R. Right? The tidal force, for example, is sensitive to R. Right? So it's once we know that we have an all uniform R, we already know that we can distinguish between different space-time points by doing specific experiments.
Okay, but at that time we cannot distinguish using a simply throwing a particle, but now you can distinguish with that.
Yes, that's right. Yeah.
The whole idea says that, as we have discussed before, that if principle of equivalence is correct, then only sitting at a point a person cannot decide that gravity is working or not.
Yeah, the instantaneous measurement will not be able to determine,
Yes.
because the measurements which only look at the equations of motion, right, will not be able to distinguish between whether there is gravity or not. But of course, if you follow it for a while, right,
Yeah.
then you can certainly distinguish.
Then that will be tracing out some set of
Part of the path, yeah,
yes,
exactly.
Space-time points.
Exactly.
But at a single space-time point, it's not
Exactly.
measuring.
That's right. So tidal force is precisely of the kind, because tidal force means that if you have two particles a little separated, right, how much force tries to pull them apart and push them together, right? So you are not performing experiments sitting at a given single space-time point, right, but two neighboring points, right? And that's why tidal forces are sensitive to minimum tensor.
But this one is allowing you to do it at the single point. That is
Yes, that's right. Yes, it is allowing you to do it at a single point. But it doesn't violate any sacred principle, because those single points are not equivalent anyway. Right? It's just that just by looking at the equation of motion, you wouldn't be able to distinguish, okay, if principle of equivalence was valid. Okay, so then so far what we have studied is the motion of particles in the presence of gravity, and yesterday we also studied through this the motion of particles in the presence of electromagnetic field. Okay, this is the general set of equations that a particle will satisfy in the presence of an electromagnetic field is given by this. Okay, we will ignore these corrections for now because they are small anyway. But now we will try to address the reverse question, that is, what produces these fields, right? You can say that, okay, we have studied the motion of particle, we know how to describe the motion of a particle in the presence of an electromagnetic field or a gravitational field, but to complete the story you also have to know how to produce, what equations determine what kind of gravitational field and what kind of electromagnetic field we have. So for electromagnetic field, the answer to this can again be gotten through application of principle of equivalence. Again, there can be corrections, as we will see, but the leading result can be obtained by simply using principle of equivalence. So what does principle of equivalence tells us? Principle of equivalence tells us that in the local inertial frame, the electromagnetic field equations, the equations that determine electromagnetic field, should be exactly identical to the equations that determine electromagnetic field in flat space. Okay, that's the guideline. So let's first look at electromagnetic field equations in flat space. Flat space, right? But we will use relativistic version of the field equations. So first of all, we already had defined F mu nu in terms of the vector potential, and this, it follows from this that we have the following equation: d mu f d rho f mu nu. So this symbol means that you have to add to it all its cyclic permutations with psi. Okay, total antisymmetric combination of d rho f mu nu is 0.
Same Bianchi.
Pardon?
It's a Bianchi.
Bianchi identity. Let me write that still. So this is what is called a Bianchi identity. Okay, it follows just by using this. Okay, if you substitute this is an identity. This is identically 0. Okay. So this basically is the sum of 3 terms, right? To begin with, it was a sum of 6 terms. But because f mu is already antisymmetric and mu and nu, all you have to do is that you have to add 3 cyclic permutations. So basically you have to, this is del rho f mu nu plus del mu f mu rho plus del okay, if you have not checked this, just substitute f and you can check. Okay. So in this sense, these equations are not very useful, okay, if you have already used this form of f. However, sometimes you don't use this form of f. Okay, you just think of f as an independent field strength. And then these equations are useful because these contain the same information that is given here. So you can forget about this and use the Bianchi identity. And these basically corresponds to the equation divergence of P equal to 0 and curl of E plus del B del T equal to 0. Then there is another set of equations which are really the dynamical equations, okay, and which do not follow directly from here. Is the equation for the source. Let me make sure that I have all the signs correct. So del mu f mu nu. Del mu f mu nu equal to minus j. Okay, if you had contracted the second index, then it would be plus. So what is J? So J0 is rho, this is charge density. And Ji is basically this corresponds to current density. So if you use a relationship between the F mu nu and electric and magnetic fields, then these corresponds to the equation divergence of E equal to rho and curl of B right. Curl of B minus okay, and of course using C equal to 1 in okay, so these are the correct electromagnetic field equations that we want to make use of. So the principle of equivalence then now tells us that in local inertial frame, we have L prime mu F prime mu rho equal to 0, but this is follows from the definition of F prime mu nu. Okay, so you either use this or you use this. Using both is you don't need, right? Because one follows from the other. But more importantly, we have the equation that del prime equal to minus J prime. Is this okay? But there is something more to it. Principle of equivalence also tells us that the rules for computing J prime, after all, how do you calculate J prime? Suppose you have a distribution of charges moving in various directions. Then in flat space, we know how to calculate J prime, right? We can calculate, and this is something we'll do later. But in flat space, we can write down an expression for J prime if we know the distribution of charges with certain velocities, right? Suppose the charges are moving with certain velocities, different charges, we know we can write down an expression for J prime. Principle of equivalence tells us that the expression for J prime in local inertial frame should have exactly the same form in terms of the charge distribution. Okay. So you are going to make use of this to write down expressions for J prime later. Okay. But right now, let's keep that in mind.
So when we talk about a charge distribution,
Yes.
it is spread out over whole space time. So
Oh, well, what we will do is we will think of a collection of particles, each moving along some trajectory. For that, we can write down the expression for J prime mu, as you will see. Right? And that expression we will first write down in flat space, and then use the principle of equivalence to lift it to curved space. Okay. But right now, let's just leave this as J prime mu, okay, without saying too much details about how to compute J prime mu. Now, given this, we can try to go back to a general frame. Well, after all, we know that in a general frame, f prime mu nu can be written as del rho x prime mu
Del prime.
del prime mu x rho del prime mu sigma f rho sigma. Right? This follows from the definition of f. F rho sigma of x we have defined in a general frame by this equation, right? So that we could simplify the charge particle equation of motion, right? That's the definition we are used to. So f prime we and f we already know. So f prime we can write in terms of f. Del prime we can write in terms of the derivative with respect to x. What about J prime? We just define J nu as del prime sigma del nu x prime sigma J prime sigma. This is the definition of J nu. Okay, every quantity has to be defined at least once, right? In fact, only once, because you don't want to have two different definitions which are inconsistent. So F we have already defined, so you don't have to do anything, but J we now define this one. Okay. So we are defining J as if it transforms as a tensor field. Okay, because once you have defined J this way, if you go to another x double prime, okay, then the relationship between the J's in x double prime and x prime x coordinate will be exactly tensorial transformation. And now I'll leave it as an exercise to check that this equation that we have here leads to d mu f mu minus g.
so capital D is small,
Capital D.
not
So here, of course, there is no difference between del prime and capital D prime, right? Because this is in a local inertial frame. Gamma prime is 0 in this frame. Okay. But when you go to the unprimed variables, right, there is a distinction, and what you get is this has a capital D. Okay, not small d, which is consistent because without the capital D, this side wouldn't have a nice tensorial transformation law. Right? This will not be, for example, a covariant vector. On the other hand, the way we have defined J nu, it follows automatically that this transforms as a covariant vector. Okay, this we can easily check. Okay, go from x coordinate to x double prime coordinate, it transforms as a covariant vector. So, from that itself, you know that having partial derivative is not good enough. You really need covariant derivative.
So we are defining that J nu transforms as a covariant vectors, but there is
Yes.
also in the local inertial frame.
No, we are just defining J nu this way. Okay, we don't say anything about covariant vector or anything. Our definition of J nu is this. With this definition, the equation simplifies. Okay. Now let's check how J nu transforms. Okay. That is not something you have said to begin with. This is just the definition of J nu. So to see how J nu transforms, we basically have to compare two arbitrary coordinate systems.
So only J prime means the prime from where gamma is vanished.
Yes.
Does J have this interpretation that J0 is rho and
Exactly. That's right. Only in that frame we know what you precisely mean by J prime 0 and J prime, right? J nu in general will have to be defined in terms of J prime. Okay. But later on, when we actually write down expression for J prime, we'll try to write a nice expression for J as well. Okay. But that's not an independent definition. This is the definition of J, and then you see what you can get, what you get. Okay. So the idea is that if we have now a different frame, right? Say J nu double prime, again an arbitrary frame, X double prime. Then J nu double prime will be given by del double prime nu X prime sigma J prime sigma. Okay, this is the same J prime. Okay, because this definition is for any coordinate system. Okay, so in particular also for double prime coordinates. And now you can simply combine these two equations to eliminate J prime. Okay, we can eliminate J prime by basically multiplying by the inverse matrix of this. And you can show that J double prime nu X double prime is given by del double prime nu X sigma times J sigma of X. Okay, now this is not something that you postulate, this is something that you prove using okay, what you postulate is what is J nu in an arbitrary coordinate frame. So this follows from these two equations. Okay, and which shows that J transforms as a covariant vector. Is this okay? There are also certain simplifications that you should note, that f mu nu is d mu a nu minus d mu a, right? This is the covariant definition of f mu nu. Okay, and this you can get again by starting with the definition of f prime and writing down f in terms of f prime. But what we can show, okay, it's a simple exercise, is that the gamma terms basically cancel between this. So this is also del mu n nu minus del mu n nu.
Here you take a transformation for A also like the vectors.
Yes, that's right. Well, you can, the way I did it, okay, there are various ways of doing it. The first, you define a mu, okay, in terms of a prime. Then you define f mu nu this way. Okay, then as long as you know the a mu transforms as a vector, f mu nu will transform as a tensor. Okay. Or you define a mu in terms of a mu prime. Okay, f mu nu independent in terms of f prime mu nu. Use the relationship with f prime and a prime to derive this relation. Okay, there you first define f mu nu and a mu independently from f prime and f prime, and then you can again show that this is true. But now what I am saying is that there is also something else which is true, that this is equal to del mu nu minus del mu. Okay. The Christoffel symbol cancels out between these two. Is this okay? And this is useful for making sure that indeed principle of equivalence holds. Because if you see that you have an equation like this here. Okay? If f mu nu involved gamma, suppose f mu nu involves gamma, this involves a derivative. Right? It has gamma of course, but it also has a derivative. So that derivative could act on the gamma that is inside F mu. Okay. So this side will now be involve various terms, of which one of them involves derivative of gamma. Now if you go to local inertial frame, the gammas will drop out, but derivatives of gamma will not. Okay. So this equation then will not reduce to the standard equation in local inertial frame. However, because of this property, okay, that in the definition of F mu, there is really no gamma. Okay, gamma term drops out. Then we can actually trust this, that this indeed is consistent with principle of equivalence. Okay, that by setting gamma prime to 0, okay, we are ensured that really we get an equation of this.
So can you repeat this again once more?
Yeah, then imagine that if the definition of F mu, okay, it's some object constructed out of first derivative of something, right? First derivative means covariant derivative, right? So it would have involved some gamma. Now, what I am saying is that if we apply another covariant derivative, then there will be derivative of gamma. Now, if we evaluate the right hand side in the local inertial frame, right?
This will not reduce to that.
This will not reduce to that. Okay, so for that it was useful that basically gamma dropped out from there. If instead of having an equation of this type, if you had, for example, the d mu mu, then the gamma term will not drop out from that, right? And this will not reduce to the standard equation for mu even in the local inertial frame.
So sir, if the principle of equivalence doesn't hold, then this definition of F mu has to be changed.
No, you can see the point you have arrived at a definition of F mu, okay, and then you stick to it because you want to maintain general coordinate design. That it's always useful to work with tensors. Okay. So once you have arrived at something which transforms as a tensor, okay, by whatever definition, then you allow for modifications which do not violate the tensorial transformation. Now it's not strictly necessary. You could say that the F mu transforms not like a tensor but in some complicated way.
Because since here the gammas are cancelling out,
Yes,
so always so the equivalence is holding.
that's true. Even if gammas are not cancelling out, and equivalence doesn't hold, you do the best you can. Right? It's an equivalence principle doesn't work, but you try to do the closest possible. Right? And that will be still assume that mu is a tensor, okay, and generalize the equation this way. Right? But in this case, once you have derivative of gamma, okay, it's not natural. I mean, you could also put, for example, d mu plus some arbitrary constant a times r plus b times plus b times r etc. Suppose this is the correct equation. Okay. So what is this? These extra terms that you are adding, okay, they are at the same. They have the same number of derivatives as the ones that come from here, because there is one of these terms here involves the derivative of gamma, right? The derivative of gamma has two derivatives of the metric. These also have two derivatives of the metric. So an equation of this sort, okay, because it doesn't reduce to the standard equation anyway, right? Even in the local inertial frame. For such equations, there is really no justification as to why you shouldn't also include these terms. Okay, but of course there can be theories in which these terms are not there. Right? Is that if you are trying to write down the most natural set of terms to a given order, say in derivative expansion, then these terms should be included with this. On the other hand, if you are doing the same thing for scalars, say suppose you have a kind Gordon field and you want to see whether principle of equivalence can be met to what? There. Here again we write the equation as d mu phi, maybe plus d prime phi, additional terms. But again the point is that this d mu phi is the same as ordinary derivative acting on a scalar. Okay, so it doesn't have a gamma. Okay, so for this principle of equivalence will hold. Okay, that if you go to local inertial equation, then equation will reduce to exactly standard equation. Okay, now there is another aspect of this equation which we will just try to use. So you have this equation d mu f mu nu equal to minus d mu. Let's try to calculate d mu f mu nu. So this is minus d mu j mu. Okay. Now this side we can write as half the commutator, anti-commutator of d nu and d mu. Anti-commutator, because the point is f mu nu is antisymmetric and mu and nu. Right? So what you are doing is that you are adding to this minus d mu d nu. Okay, just extending the indices mu and nu. Another way of saying this is that d mu. See what have we added here? We have added a minus d mu f mu nu, right? Okay, this is extra term we have added here. Okay, if you take d mu anti-commutator, then the original term was d mu f mu nu. Okay, I have added a minus d mu f mu nu. But this is the same. You can just exchange mu and nu. Okay, mu and nu are dummy indices anyway. So this is minus d mu f nu mu. But f nu mu is minus f mu. So this is minus d mu f mu. We just exchange mu and nu index because f nu mu is minus f mu. So this is plus d nu f mu. So basically, what you have done is that if you take this commutator, the extra term that you have is the same as the original term because you add it and divide by half. Is this logic clear? Right? Because it's antisymmetric in mu and nu, you can just replace this by anti-commutator of d nu and d.
This will be anti-commutator.
This will be?
Anti-commutator. Curly brackets.
Sorry, commutator.
Yeah.
Yeah.
This d mu minus d mu d mu.
Yeah.
Yeah. This is commutator. Okay. Yeah. This is whatever you have defined this to.
Yes.
Okay. So now we use the fact that if we take d mu, or let's say d mu, f alpha beta. So this had two terms minus r alpha sigma mu f sigma beta minus r beta sigma mu f sigma. Okay, we had written down a relation of this type for a general tensor earlier. Okay, we are just writing the specification of this. So now we are going to raise this index. Okay, that means raising the index. Okay, because raising index can be done inside covariant derivatives. So d nu, the commutator of d nu with f. Now for alpha and beta, I am going to substitute mu and nu. Okay, so I am just doing two steps at one go. The first is that this index mu nu I will raise. Okay, in both places, and then you replace alpha by mu and beta by nu. So this is given by minus r. So first let me raise this index mu nu. Alpha has become mu, sigma, f sigma nu minus r, again mu nu index is raised, so beta has become nu, sigma f nu sigma. Okay, so this is minus r mu contracted, so r sigma nu, this is the Ricci answer, f sigma nu minus this one nu contracted. Okay, so this is not the correct place, so we first exchange mu and nu.
So sign will change.
Sign will change, so that's plus r. So now you have brought in the correct place, so sigma mu, r sigma mu. But both of these are actually 0 because this is symmetric, right?
And
This is anti-symmetric. Okay, so this is 0, similarly for this. Okay, so this is 0. Is this okay?
so the current is conserved.
Yeah, so this means if we now substitute back here that d nu j nu, so this means that d nu j nu is equal to 0. Okay, the current is conserved. Okay, this is the law for current conservation. Now, of course, j nu is something that is not up to us to choose, right? J nu has to be defined in terms of j prime, right? And j prime has to be constructed by following the same rules as the flat space dynamics. Okay, that was the principle of equivalence. So now we can ask that does this hold automatically, right? What is the equation that guarantees this that this will hold? Okay. And the equation that guarantees that this will hold, that it follows from del prime nu j prime nu equal to 0. Okay. This is the current conservation law in flat space time. Yeah, in flat space time we know that when you produce electromagnetic current, okay, for consistency, this is always conserved. So the construction of j prime nu in flat space guarantees this equation. And then you can show that as a consequence of this, and using the fact that j nu and j prime nu are related in some specific way, that this implies this. Okay, so this d nu j nu equal to 0 is not a independent equation. Okay. First of all, it has to hold for consistency, and second, that it follows from the usual laws of current conservation in local inertia. So you can also see from here that things are tightly related, right? Suppose in the local inertial frame you change the form of j prime. Okay, we said that I'll use only half of equivalence principle, okay, namely that the electromagnetic field given in terms of J mu, okay, that equation will remain unchanged. Okay. But J prime mu, how we construct in the local inertial term, I modify it. Okay. Then in general, that modified J prime mu may not satisfy this equation, okay, and that will make this whole thing inconsistent. Okay, so you have to make sure that you have a consistent theory in the local inertial frame, consistent set of equations of motion in local inertial frame, which will follow, of course, automatically if your equations are induced from flat space dynamics, okay, where you have already checked consistency. Then you transform everything to a general coordinate frame.
Like bottom to top approach.
Well, bottom to top meaning it just says that that if you are using principle of equivalence, you have to make sure that in the local inertial frame, all the identities are satisfied, right? All the flat space identities are satisfied. If only half of the identities are satisfied and the other half are not, then you will run into inconsistency in general. Okay? So here, if we had dropped this equation from the flat space, if you had said in local inertial frame, the relationship between F and J will be given by this, will be given by del prime mu F prime mu nu equal to minus J nu minus J prime nu. But del prime mu will not satisfy the equation of this kind. Okay, then you will run into inconsistency.
So, but this is a consequence of the above equation only. So
Yes, except that, I mean, at this stage, okay, that you have to, let's say, we can formulate that this involves two derivatives, right? So when you take another derivative, okay, it could be that it's not a consequence of this because there are other derivatives. So when you this only holds locally, right? Okay. When you take another derivative, right? This is not guaranteed that the left hand side is 0. You see, because you are saying that because this is this, okay, now I apply del prime mu on both sides, right? Okay, but del prime mu means what? Del prime mu means that you have to take this, take its neighboring point and take the difference, right? But a neighboring point, this equation doesn't hold, right? Because this equation is a local equation, it holds at that x prime point, right? The neighboring point, local inertial frame is something different. So it's not completely guaranteed from here that this will hold in the local inertial frame, right? At least a priori you cannot guarantee it. Okay? The reason that it works, okay, that this naive approach that you just apply del prime mu and it will work, okay, is again because of this fact that when you do this calculation, the Riemann tensor part vanishes, right? But here you have to do some calculation to make sure that the Riemann tensor part doesn't contribute. Okay, without this additional knowledge, okay, we cannot conclude that this implies this. Is this okay? In flat space, of course, this follows from this equation, right? In flat space, this holds everywhere, right? In a single coordinate.
Sir, but in this context, can we talk about similar perturbative extensions to this dynamical equation in the case?
Yes, you can. So the point is, you can say, suppose d nu j nu is not 0 but something else. Okay, then you can do this. Suppose there are some terms of motion Riemann tensor. Okay, but then you have to make sure that you also add an appropriate quantity.
It cancels that because
Here, exactly. That we have a d mu f mu nu equal to minus j nu, right? So you have to add something else to this equation also. If you want to modify j nu so that d nu j nu is not 0, but some terms involving Riemann tensor, you have to also add something here, so that when you take d mu on both sides, there is a contradiction.
So basically you're saying that even if I have an extension to this one, when
Yes.
I go to the back to the local inertial frame, I should get back del mu J nu equal to 0 because charge conservation is sacrosanct, right? That should not be violated. Is that the reason?
Well, no, charge conservation is sacrosanct, but local charge conservation is not necessarily valid, right? So it could be del mu J mu plus del mu of something else equal to 0. Yeah, that will be still be consistent with charge conservation. Right? It will just say that J, so that basically says J mu is not actually what is measuring your charge density. There is some additional source of charge density somewhere else, from some other source. Right? So it is true the integral of del mu J mu should vanish. Okay? But that can be satisfied by del mu J mu plus del mu of something else equal to 0.
So I am not getting that again the term which you are writing. Del prime mu. Del prime mu is something which you are doing locally, right?
But
Like
see,
previously
this-
also when you are doing a del prime mu, that thing is you are doing locally.
yes, that is true, exactly. So that the reason that we could do it locally is because we shouldn't have been able to do this. Okay? But the reason that we can do it is because from f prime mu the gamma is disappeared. Okay. Otherwise, you could have asked besides suspicions even at this stage. Okay. If instead of f prime mu nu, right, if you just had del prime mu or a prime nu, okay, then it would be suspect even at this stage. Okay, because you are taking two derivatives. Okay.
So it's like your Maxwell's equations are actually allowing you to do such stuff.
Exactly. Yeah. Your Maxwell's equation. So the that's why the equivalence principle you cannot also always maintain. Right? In
Maxwell
equation,
equations is allowing you to have a equivalence principle. but
Exactly.
You cannot always.
you cannot always expect that you should have an equivalence principle of this kind. Right? There can always be terms that if you have second derivative, right, the fact that you can always get rid of the first derivative of gamma is not guaranteed. Right? It is true for Maxwell's equation, it is true for scalars, but there are maybe other fields where it's not true. Okay, so where you cannot get rid of first derivatives of gamma from the equations of motion.
So if you have a new theory in which you have some random equations,
Yes.
so how you will then raise them to your PTR? You cannot.
Well, you can by giving a principle of equivalence, but still you use the intuition, okay, to write them as tensors, okay, and then try to write down the most general covariant equation involving those tensors. Okay. See, one way of doing this is you write the flat space equation, okay, then say that you simply replace all the partial derivatives by covariant derivatives. Okay, that will be one possible way of generalizing this to general derivative, even though it may not satisfy equations by the equivalence principle.
So, but if you are simply taking a flat space equation and changing it to your
Covariant
covariant
derivative.
derivative,
Yes.
there can be some R terms which were there in your equations which.
Exactly, that's true. So that's why you cannot uniquely determine. So first of all, equivalence principle is not valid, okay, and then you may not be able to uniquely fix the terms, because as you said there can be R terms, right, which are the same order, okay, which are there, which should not be there in flat space. Right? So that's why for if you are trying to generalize an equation of the form d mu nu or del mu nu equal to 0. Del mu nu equal to 0. Okay, suppose you are trying to generalize this to curved space. There is no unique generalization, right, which is natural, because equivalence principle doesn't hold anywhere, right, because you have the first derivative of gamma mu from the second derivative, and hence when you generalize to curved space, you write it as d mu, but you can also add r times a mu and r mu nu a nu. And those terms are equal as natural as the terms which are contained in d mu. Is this okay? Now this doesn't mean that an actual field, even though equivalence principle is holds, okay, that equivalence principle is good for Maxwell field. Okay, it may not be good. In fact, in general, we expect that there will be corrections. Okay, but those corrections are again of high order.
In Maxwell's equations also.
In Maxwell's equation also, exactly. Are there any other questions? Okay, so now we turn to the next question, which is that how to generalize this for gravity. Maybe I should also add that when we try to generalize, right, of course equivalence principle or in the absence of equivalence principle is general covariance is one guideline. But sometimes we also have other symmetries which are good guidelines. Okay. For example, if you are using Maxwell field, then you know that there is the original Maxwell's equation had a symmetry under a mu goes to a mu plus partial mu of lambda, right? The gauge symmetry. That's why everything depends on a mu. Now you may say that you want to maintain that symmetry. Okay, that you don't want to destroy that. In which case, terms like that, if you, for example, try to correct this by writing something like R mu mu, R mu rho f. These corrections are perfectly consistent with general coordinate invariance, but not with the symmetry under which a rho goes to a rho plus partial rho of lambda. You can demand that everything depends only on f.
So we demanded that if my f transforms as the transformation law means how I defined if
Yes.
it transforms like a tensor.
Yes.
We inherently use that property that means under a
Yeah.
going to a mu plus.
So, yeah, so f mu is infinite and a mu goes to a mu plus del partial mu lambda, right? But suppose now we want to say we want to generalize this without worrying about this symmetry. Okay. Suppose somehow interaction with gravity breaks that symmetry. In which case these terms will be allowed. Right? So if there is, you have reason to believe that the interaction with gravity breaks those symmetries, then you have to allow terms like this. If on the other hand you have reason to believe that the interaction with gravity does not break that symmetry, then these terms are not allowed. Yeah, you have to only build equations of motion from f minus.
Which means is there no general notion which will tell us that these symmetries will be there and this won't be there?
Well, yeah, of course there is, I mean, when you build a theory, there are, it's highly constrained, right? That if you break that symmetry, right, then a lot more thing, you have to do a lot more thing, right? You have to make that field massive, for example, right? There is a way to make this, make it massive, okay, and break that symmetry, that manifest symmetry. You get the gauge field massive. Okay, so for massive gauge fields, you can have terms like this in general. Okay, but this is not a generic story. Okay, case by case, you have to see what are the symmetries that you want to maintain, and then you see what are the possible terms that you can add to the equations.
But can we say that unless we are going into the realm of quantum mechanics of gravity, we are safe?
Typically, that is true. Okay. On the other hand, it is also true that if we allow terms like this, mu rho f, a rho, these are not subspace compared to the terms that we have already included. Okay, because the terms that we have, if you look at d mu, d rho, a mu. Of course, the leading term here is just ordinary derivative. Okay, that term is the dominant one. But the first order effect of gravity comes from gamma, right? Okay, that involves two derivatives, right? Either two factors of gamma or one derivative of gamma. That typically is of the same order as this, because this also has two derivatives. Okay. So if you allow terms like this, okay, then these terms may not be suppressed compared to the terms that come from here. Okay, the gravitational terms which come from here. So in this sense, these terms are not as small as the ones that involve only F mu. Right? Because the ones that involve only F mu already has more derivatives. Right? Where F mu has one derivative, one extra derivative compared to A. Okay, and then by Lorentz invariance you can see that you also have to include more derivatives in R. So typically the idea is that when you build a theory, you first identify the symmetries, right? Then write down all possible terms, and then you see whether the coefficients are large enough to be observable, right, in a given experiment. Okay, so now we want to generalize to gravity. Okay, so what is the question? We want to see how to write down the field equations that determine what the metric is. Now here of course you cannot use principle of equivalence. Okay? Because principle of equivalence says that in local inertial frame we can switch off gravity, right? As if there is no gravity. Okay? That certainly is not a very useful starting point if you are trying to describe the gravitational field equations. Okay? So what we will do is to instead start with some intuition, and that is the first constraint that you have to satisfy is that in the weak field non-relativistic limit, this equation that we are looking for must reduce to the standard Newtonian gravity equation. Okay? So in weak field non-relativistic limit, we have the equation del square phi is equal to 4 pi g times, well, I should use rho probably, okay, let's call it rho m. Okay? This is the mass density. So the goal is then to try to generalize this equation. Okay, or try to use this as a clue to see what equation it could come from. Okay, in terms of the metric. So we try to guess which possible terms could give rise to these two sides of the equation as it stands. Now we know that in this limit phi comes from h naught naught. Right? H naught is minus 2 phi. So this looks like having two derivatives of the metric. So the left hand side must be something constructed out of two derivatives of metric. On the right hand side we have mass density, rho m. Now we want to see what is its generalization, okay, what it could stand for, and in trying to identify what it could stand for, okay, one can quickly realize that this mass density is not a very nice thing. Okay. Why is it a nice thing? It's not a nice thing because it's not additive. Okay. So let's imagine that we have a hydrogen atom. Hydrogen atom, okay. So it has a proton and the electron, and let's suppose we want to study the mass of the hydrogen atom. So naively you would think it's Mp plus m. Okay, but this is not strictly true. There is a binding energy. So imagine that we really have mass density on the right hand side, okay, and you have a proton and an electron. Then we would ask whether it's this which should appear on the right hand side or whether it's this which should appear on the right hand side. Okay. Whether the mass of the hydrogen atom that should appear or the mass of the proton and electron that should appear. So the correct way to interpret this is that this is, even though in the classical Newtonian theory, the right hand side appears as mass density. What really appears on the right hand side is energy density. Because if you think in terms of energy, then there is no confusion. The energy of the system is the sum of the total energies. This and this. So we think of the energy as a source of gravity. Even though in the classical Newtonian gravity, there is really not much difference between mass and energy. Okay, in non-relativistic limit, most of the energy comes from the mass. Okay, the kinetic term is negligible compared to rest mass energy. But when we try to generalize it, so you have to make a decision as to whether to use mass or energy. And there it's much more natural to use energy as the source. Because then you don't have to worry about whether the binding energy, okay, should correspond to a source or not. Okay. If it's a mass, then you worry that if the mass, then it must be sum of masses of the protons and electrons. These are the elementary objects, right? Okay, but then you are leaving out binding energy. Okay, so you violate the equality of the inertial mass and the gravitational mass, right? Because the inertial mass certainly is a total mass. Okay. So from all this viewpoint, we can argue that this side should be replaced by energy density.
Then it becomes additive.
Pardon?
Then it becomes additive.
Yes, then it becomes additive. Okay, two different sources of energy density gives you just adds. So what? Now we also want to try to think of this as in a covariant fashion. Now we know that in flat space, the energy density would correspond to, would come from energy momentum tensor. Right? Energy density by itself doesn't transform nicely under Lorentz transformation, but it's the energy momentum tensor which transforms nicely under Lorentz transformation. Okay? So in flat space, we have P mu. And we know precisely how to calculate energy momentum density. Okay, given a distribution of particles, okay, with various momenta, we can explicitly write down an expression for the energy momentum density. Okay, we'll do this later, maybe tomorrow. Okay, but it's clear that if you know a distribution of particles with certain, each carrying certain momentum, we can write down an expression for the energy momentum density of the system.
That will be most general ideal fluid energy momentum.
Yeah, but you can, instead of using fluid, right, you can think in terms of the limits of particles, because you have to see what energy momentum tensor means in terms of microscopic objects, right? See, if you think of the microscopic objects as particles moving around, then you can just sum them, right? Or you can consider the energy momentum tensor as an electromagnetic field, for example, right? That's another possible source. Okay. So, the point is that in flat space we have definite rules for computing energy momentum tensor. So now we define the energy momentum tensor in the presence of gravity, okay, in the following way. That you first go to local inertial frame. Okay? If you go to local inertial frame, then we use exactly the same rules that we use for in flat space to define a T prime mu nu. Okay? Right now it's sort of in a tensor, right? T prime mu nu is defined precisely in local inertial frame. So in local inertial frame,
Here we are using principle of equivalence.
well, this is just a definition. So, yeah, you can say we are using principle of equivalence, but unless you have put it in an equation, right, it's not a principle, right? You are just defining T prime mu nu in certain way. Okay? So, in local inertial frame, define T prime mu nu as in flat space. Okay, or T prime mu nu or T prime mu nu, just matter because there of course you raise and lower index by eta. Now in general coordinate system, we define T mu nu as del prime rho x mu del prime sigma x mu T rho sigma T prime rho sigma. Is this okay? This definition of T mu nu guarantees that it transforms like a tensor. This defines T mu nu in all coordinate system, right? X coordinate, x double prime coordinate, x triple prime. Then you can go from x double prime to x. Okay, forgetting by eliminating the x prime coordinate altogether. And that transformation law is like a tensorial transformation. Okay, T mu nu versus T double prime. Is this okay? So we have introduced something which transforms as a tensor in the presence of gravity. Okay, we have constructed it by this very specific method, starting from local inertial frame, where you know how to construct energy momentum tensor. But then, after you have constructed this, but from the definition it follows that it's a tensor. So we attempt to get generalize this equation, okay, to get the full equation for determining gravity by replacing the right hand side by some constant as T. Some constant. What about the left hand side? Left hand side, okay, so this equation has to be covariant. Then if this is a tensor of rank 2, okay, rank 02, then the left hand side better also be a tensor of rank 02. It has to be constructed out of two derivatives of the metric. Okay. Now we know that if we consider the functions which involve two derivatives of the metric, then all the invariant information is contained in the Riemann tensor. Right? Because the number of Riemann tensor, the number of components of the Riemann tensor is counted, and that's exactly the number of coefficients that you cannot set to 0 by using coordinate change. Right? So Riemann tensor contains all possible information involving two derivatives of the metric. So whatever be the left hand side, it has to be constructed out of Riemann tensor. But it has only two index. Right? It's a rank 02 tensor. So the only possible thing that you can do is to take it a linear combination of B R mu nu plus C R G mu nu. Okay, where B and C are two constants. And there is nothing else you can write down on the left hand side which has two derivatives of the metric. Okay, and which transforms as a tensor of rank 02. Is this clear? Now this B you can drop. Why? Because after all there are three coefficients, right? So one overall coefficient you can always take away. And by dividing by B, you can just divide the whole equation by B, declare C by B as your new C and A by C as your new C. Okay, so this is the form you can use. we go back to our definition of energy momentum tensor, and now we run things in reverse of what we did for electromagnetism. Okay, for electromagnetism, we said that we had d mu f mu nu equal to j nu, and from there it followed that d nu j nu equal to 0. And then we argued that that follows actually as a consequence of the way you construct j nu from a local inertial frame. Now, the analog of that doesn't exist here because we still don't know what the right hand, where the left hand side is. Okay. But you know the right hand side is T mu nu. Okay. So you can see, are there such T mu nu satisfying a conservation law in flat space? Because if it does, then one can expect that when you generalize this to local inertial frame, the same conservation law should hold. And then we can go back and see what it implies for this equation. So, assuming that del prime mu t prime mu nu equal to 0, it's a simple exercise to check that d mu t mu nu equal to 0. So this means that we should have d mu of r mu nu plus a r g mu nu.
So, this conservation equation is true only for homogeneous and isotropic.
No, no. As long as this holds, it's not true. I mean, if you look at the flat space equations, right? It's not true only for homogeneous and isotropic distribution. Energy momentum tensor is conserved. It's simply because the total energy has to be conserved, right? Okay. In fact, we'll next time we'll write down explicit expression for T mu nu in terms of particle distribution, and there you will see that the conservation law holds automatically. Okay. As long as the particles satisfy their own equations of motion, okay, the conservation law will hold automatically. So this has to be true.
This we have proved from the Yankee identity.
Yeah. So the point is that there are two philosophy you can take. The one is that this is an additional equation that you have to satisfy. Okay, meaning it's a consequence of this, of course. But you may take the viewpoint that this is an equation that you have to satisfy. This gives some constant on the metric. Right? Because after all, you are trying to find an equation which determines the metric in terms of the matter distribution, right? So this could give some additional constant on the metric. So that's one viewpoint. The second viewpoint is that you have to make the equation in such a way that this is identical to 0. Okay, these are two possible scenarios. Now what you can show, okay, I will not go do that here, that if this gives additional condition on the metric, okay, which will be the case for arbitrary A, okay, then in general these set of equations will have very few solutions. Okay, there may be only spatial solutions but nothing else.
So can you repeat?
That if you take a generic A, then this equation will put some additional condition on the metric. Okay, these equations will not be trivial in that case, right? These will not be identically satisfied. In such cases, okay, the metric is so tightly constrained that there are almost no solutions. Okay, except maybe some very special ones. Okay, flat space in absence of any matter, of course, is a solution, right? Because then it doesn't matter what A is. But there are very few solutions if you try to, unless these equations are also identically satisfied. Okay, if these equations are identically satisfied, then these equations are not relevant. Okay. And then the original equations, okay, you have to look at the other components of the original equations which will still constrain the metric. Okay. So a consistent set of field equations can only be obtained if this is identically satisfied. Okay, otherwise you can write down a set of equations but they will have very few solutions. So now we know that if we want to satisfy this identically, then the coefficient has to be fixed in certain way, namely A must be equal to minus half. Right? That we had seen, this is the Einstein tensor, and that this vanishes by Bianchi identity. Okay? So this essentially fixes the right hand side, the left hand side. Okay? So R mu minus half R G mu is equal to some constant A plus T mu. Is this okay? Finally, you have to fix A. Right? A is still an unknown constant.
Take 0, 0.
Yeah, so to fix A, we go to the weak field non-relativistic limit. Use the fact that G00 in this limit is minus H, minus 1, minus 2 phi. Right? Again in C equal to 1. Okay. And just evaluate the 0, 0 component of both sides. Okay. What we will find is the equation y del square phi equal to minus half A rho m. What is rho m? Rho m is T00. Here as you can see. And now we compare with this. That fixes A to be minus 8 pi g.
Can you repeat?
Yeah. So the point is we have this. So we arrived at this form of the equation, right? Now A is the constant that is unknown. Okay, you have to find this constant A. So what we do is that we now see what this equation becomes in the weak field non-relativistic limit. So this weak field limit corresponds to when G00 is minus 1 minus 2 phi. We have already identified this as a gravitational potential for the particle motion in this background. And so we take this equation and look at the 0, 0 component. Okay, we compute R00 in terms of the metric and its derivatives. We compute R in terms of metric and its derivatives. Substitute here. Using the fact that we are only keeping first order and H. Right? All second order terms are equal. After doing this, we will find that the right hand side, well, if I can do it this way. Okay? In right hand side, you will find minus 2 del square phi equal to A rho m. Okay, I am keeping A as it is because there is A T mu, so T00 is rho m. Okay, energy density, or which is the same as mass density in the non-relativistic limit. So this object on the left hand side, the 0, 0 component, becomes as minus 2 del square phi. Okay, so in this limit, the equation becomes minus 2 del square phi equal to A rho m. And now the idea is that we want to make sure that this reduces to the standard Newtonian equation, right? Because in this limit, you better get back the Newton's laws. That's here. So if you compare this, we get A equal to minus 8 pi g. So with this, then we can write down the final Einstein's equation. R mu minus half R G mu equal to minus 8 pi g. But I should say that this convention that I am using, okay, is the one that Weinberg uses. But there are various different conventions that different books use, and they all differ by sign. Okay. So, I think Wikipedia has a article on Einstein's equation, and there you will find the various sign conventions, the different books, and which books use what sign convention, right? So it has compared the sign conventions used in different books, right? So if you are reading some other book, you just look at Wikipedia and match your sign convention and fix the signs once or one, right? So using that you can translate from between the convention between different books.
So one question is that if we, in general, without looking at the Newton's equation, we see only that equation if T mu is in the right hand side, this
Yes.
T mu plus some constant times G mu.
Yes.
And also this mu.
Yes. So it will not. So it will. That means it reserves covariance. Right? T mu nu plus some constant times T mu nu. But what you can do is you can include that in the definition of T mu nu. Instead of saying it's T mu nu plus some constant times T mu nu, we can write T mu nu as whatever it is plus some constant times G mu. Right? This doesn't violate conservation law because d mu T mu nu, right? If this is conserved, then d mu G mu nu is automatically conserved. So this is certainly an allowed addition. Right? And this is what we call cosmological constant. And even in the absence of matter, okay, because you have cosmological constant, there is always a constant energy density that is source in T mu nu. Okay, but this is very, very tiny. So for like studying solar system, you can just ignore that constant.
Sir,
Yes.
the thing like del prime mu T prime mu nu equals to 0
Yes.
is something in special relativity, right?
Yes, that's right.
And then you are coming to a, you can show that capital D mu, capital T mu
Yes.
should be 0.
That's right. So as long as this is valid,
True.
right, you can show that this it follows from this. This follows from this. Because once I have started with this, the T mu nu I have defined in terms of T prime mu nu, right?
Yeah.
This we know the relationship between G mu and del prime.
Yeah.
Okay, so you can show that this follows as a consequence of this.
Yeah, so you can say that this is a geometric consequence which is coming here, d mu T mu nu equals to 0. Right, this is because of your geometry or the way you have defined your Riemann geometry, right?
Yes, okay, I don't know what is the meaning of, so if this is geometric, then yes, this is geometric, but this is not necessarily geometric, right? This depends on the,
I'm saying in special relativity where in flat metric you have such a relationship.
but that's not geometric, this is not geometric, right? Even in special relativity,
Huh.
this is a dynamical equation,
True.
right? With the particles that are moving, for example, they have to satisfy their own equations of motion for this to be valid.
True.
Yes.
So if that is valid, then that thing is valid.
Yes, exactly. That's right. So,
But that thing is in
Curved
curve
space.
space.
exactly.
So when you were writing such an equation, then you can you argue from this that A should be minus half? That's what I'm thinking.
From this,
Yeah, because capital D mu T mu is 0 and it
Yes.
is coming because of your simply taking a curved space time.
well, it's not simply because of curved space-time, right? It does use some non-trivial input from the dynamics of the particles, right? So it's not completely geometric, right? It is true that this is something that holds automatically once a particle satisfies its equation of motion, right? And that's the reason why we have to make sure that this is satisfied identically. But it's not pure geometry that's giving this, right? Because T mu nu is not completely a geometric object.
The left side is pure geometry.
Yeah, left side is purely geometric.
The
Right side is not.
So left side is coming as a consequence of a geometry. That's what I'm.
Yeah, so left side is purely geometric, certainly. But to argue that if A is not equal to minus half, right? In which case this equation will not be identically satisfied, but it gives some additional condition on the metric. Right? That those set of equations are too many to satisfy. Right? That requires some effort, right? I mean, it's not absolutely straightforward just by looking at this. And otherwise, you will say, okay, who cares? You write down some R mu nu plus some arbitrary constant R G mu nu equal to this, right? And if this constant happens to be minus half, then the d mu T mu nu is automatically satisfied. If it's not equal to minus half, then it gives some additional condition on the merit. Right? You can always take that viewpoint. Right? It's only after you have started pushing and seeing what its consequences are, then you discover that these are inconsistent set. Okay, so I think I'll stop here and then continue.